Good day, everybody. This is Orekoya Fumi Olusegun, Physics Mathematics Fundamentals on YouTube. Today, we are taking a topic under physics, and that topic is related to the dimension in physics. So, today, we are working on a topic derivation of the equation, of the period of a pendulum bulb by dimensional method. So in this particular problem, uh, assuming that during the experimental procedure, we come across these three variables: length, mass, and acceleration. The length of the pendulum bulb, the mass of the bulb, and direction due to gravity. So I'll just make a sketch to illustrate what I mean by the pendulum bulb. Let's say we have a support that we tie a string to. This is the support, and this is the string. The string is like a suspension material. So this is the bulb. This is the pendulum bulb. And then, according to what we have here, we are given that one of the variables that depend on the period t of the pendulum bulb is the length. So we talk about the length of the pendulum bulb. Let's say this is the length L of the pendulum bulb. This variable we want to work on using dimension. Then the mass M of the pendulum bulb. And then this particular mass is being acted by a force of gravity. That's the weight. So this particular weight now, which is the force of gravity, is given as a mg. So in this case now, the weight is the one that is telling us that there is a mass, and there is a particular acceleration due to gravity, which is a constant, pushing this particular pendulum bulb towards the earth. So the variable that we identify in this experiment as this pendulum bulb is oscillating to and fro. We want to derive the formula for the time t taken for this particular pendulum bulb to complete a full cycle. So that means the cycle of starting from here, going this way, coming back to this particular position, then going this way, then coming back to this particular position. That's the full oscillation or full cycle. Oscillation or cycle. So what time will it take? I'm talking about the clock now. What time will it take, time t, for it to complete this full cycle? Now, according to the variable that I mentioned here, we say the time t is proportional to the length L, let's say raised to power x, which we don't know. Then mass M of the pendulum bulb, let's say raised to power y, which we don't know. Then it's also proportional to the acceleration due to gravity. Let's call this one g raised to power z. So if you remove this sign of a proportionality sign, this particular proportionality symbol, we are going to have t is equal to k L raised to power x, m raised to power y, then times g raised to power z. And then this particular g, we need to write it in dimensional form. And we know that g is more or less the directed distance. That is the displacement. It's the displacement per unit time. So that is velocity per unit time. So acceleration is changing velocity per unit time. And then we know that the dimension of velocity itself is defined as displacement divided by time. So, and this displacement in dimension form is L, and this time in dimension form is t. And we know that for the g, which is v all over t, the dimension of v is what I have here, L over t. So we write L divided by t, then divided by this t again. So that means we are going to multiply this one with another t. So that means the dimension of this g will now be L. Using t times t will give you t square. So when we take it up using the law of indices, it becomes negative. So when you take the t square up, it becomes t raised power minus 2. So this is the dimension for the acceleration due to gravity. So I'm going to substitute this expression now of g back to this place now. So that means the period t of the simple pendulum bomb. Please take note, this t is the period of the simple pendulum bomb measured in seconds, and this particular period is the time taken for this pendulum bomb to oscillate fully. That means to complete a full cycle. So now this our period t cannot be taken as k L raised to power x times m raised to power y. Then instead of this g now, we are going to put this one. That is a lt raised to power minus 2, everything in brackets, then raised to power z. So if you open these brackets now, we are going to have our t is equal to k L raised to power x m raised to power y. So we have, when you open this brackets, it's going to be L raised to power z times t raised to power minus 2z. Now since we have t there, we have t here, then we have since we have L here and L here, we can combine these two powers together. So let me rewrite. T is equal to k. This L and this L, they are multiplying. There is a multiplication between them. So that means we are going to have the power x and z. So it's going to be L raised to power x plus z. Then times t raised to power minus 2z. Now, k is a dimensional, this thing is dimensionless because it's a constant. So k can be excused from this particular relationship. So we can now write our t now in terms of dimension. This t cannot be written as L raised to power x plus z, t raised to power minus 2z. Now we know that the dimension of t time t is already t. So that means t raised to power 1. So we now compare this particular side of the problem is equivalent to this particular side. So we compare the power. When we look at this t and t here, the power will be 1 is equal to minus 2z. So to get my z here now, the z will now be minus, dividing both sides by 2, going to be minus 1 all over 2. That is for the z. Now to get the other one, you know that here there is no L in this side. So that means we are going to equate this power to 0, because this one, if you want to allow L to stand here, it's going to be L raised to power 0. So we compare this power here with that of L on this other side. So it's going to be x plus z is equal to 0. Since my z is already minus half, I can write x, my substituting here, going to be minus half is equal to 0. Therefore, x is equal to half. Now, I already gotten my x and z. Now, for the m, this particular m here, there is no m here, so it's like m raised to power 0. So when you compare, the y will be equal to 0. So now, since I've gotten all my units, I mean the power here, this power x, the power x, y, and z. Since I've gotten my x, y, and z to be this value, the x is half. So the y that I got here is 0. When you compare this power to this other side of the equation, that's how I was able to get all these equations out. So my y now that we have gotten is 0, and the z that we got here is minus half. So since we've gotten this parameter here now, we can now rewrite what we have here as t is equal to L raised to power x plus z. and my x is half. That is half plus z. My z is half, so that's going to be minus half, then times plus 1, because when I put this thing here, the z here, that's okay, L, okay, times minus half, then we have t minus 2 times the z here is minus half. So minus half times minus 2 give us minus times minus plus 2 times half will give us 1. So this become t. And then this L that I have here, you know that we have gotten our x before. We have gotten our x before to be minus half, and our z also minus half. So minus half times minus half here will give us plus. So the L will be raised to power 1. So this t that I have here, 2 times half will give us 1. So I'm going to have, then for the acceleration due to gravity, that is my g. So, this substitution supposed to be put in this place. So I can write my t is equal to k L raised to power x m raised to power y then with a g raised to power z. So but I can put it like this: k L raised to power x, the x that we got there the other time is half, then m raised to power y, the y is 0, and g raised to power z, the z is minus half. So we can see now here that t is equal to k L raised to power half. This m raised to power 0 means the time t of the simple pendulum does not depend on the mass of the pendulum. So m raised to power 0 is 1. So we are left with g raised to power minus half. So now the period t is equal to k L raised to power half. This g raised to power minus half is same thing as g raised to power half. And then the meaning of square root symbol that we have here, let me put everything here for us to see. T is equal to k L raised to power half, everything g raised to power half. So in law of indices, power of half means square root. So we are going to have k square root of L all over g, all over square root of g. So square root of L over square root of g will be square root of both of them, L all over g. So that means t, which is the simple pendulum, is directly proportional to the square root of the length of the pendulum divided by the acceleration due to gravity. Through further experimentation, k has been found to be 2 pi. So when we put 2 pi here, we are going to have t is equal to 2 pi square root of L divided by g. So this is the proof of the formula for finding the period t of a simple pendulum. This is Orekoya Olusegun, Physics Mathematics Fundamental on YouTube. Thank you for having your time. Have a nice day. Bye.